In this lecture, we will discuss the uses of Ka and Kb and the relationships between them. This material will serve as an introduction to the discussion of weak acids and weak bases. We will begin by discussing calculations involving Ka and Kb. Lastly, we will introduce pKa and pKb and discuss their relationship. We learned in a previous lecture that the relative strength of an acid is determined by how well it dissociates in water to donate its proton. A strong acid will completely level in water, donating all of its protons. A weak acid, on the other hand, will only partially dissociate in water. Most of the weak acid will stay in its protonated form. The degree of dissociation of any acid is determined by the value of its acid dissociation constant, Ka. The larger the value of Ka, the stronger an acid is, and will have a greater extent of dissociation. For example, strong acids have a Ka value considerably greater than 1. If we consider nitric acid, it has a Ka value of approximately 25, whereas hydroiodic acid has a Ka value that is approximately 3 times 10 to the 9th power. Most acids have a Ka value less than 1. These are considered to be weak acids. For example, acetic acid has a Ka value equal to 1.8 times 10 to the negative 5, while boric acid has a Ka value of 5.8 times 10 to the negative 10. Note that because acetic acid has a larger Ka value than boric acid, we consider acetic acid to be a stronger acid than boric acid. All weak acids exist in a state of chemical equilibrium. Consider the reaction of the weak acid HA with water. We have HA aqueous reacting with water to form in equilibrium hydronium ions plus A- ions. The equilibrium constant expression takes the form Ka is equal to the product of the hydronium ion concentration times the A- concentration divided by the HA concentration. As in the previous chapter, there are two types of calculations that we can perform. First, if we know information about the equilibrium concentrations, we can calculate the value of Ka. Secondly, we may know the value of Ka and enough information that we can calculate the equilibrium concentrations and the pH. In this lecture, we will focus on the first type of problem. Recall from the previous chapter that if we know the initial concentrations for all of the species in an equilibrium reaction, and we can determine the equilibrium concentration of at least one species, then we can calculate the value of K. This is true for weak acids and bases as well. If we know the formal concentration of the weak acid and the value of the pH, then we have sufficient information to calculate Ka. Let's build a general equation to allow us to calculate the value of Ka from the information that we need. As before, we begin with our ICE table for our weak acid HA, which has a formal concentration of F sub HA. We begin with our initial conditions. Our initial concentration of HA is just the formal concentration, and we assume that we begin with 0 molar of H3O plus and A minus. As always, because water is a pure liquid, we ignore it in our ICE table. We can begin to fill in our change row. We know that we must lose HA to form H3O plus and A minus. Since the stoichiometric coefficients are all 1, this means that HA decreases by x, H3O plus and A minus both increase by x. And this gives us our equilibrium row. Our concentration of HA at equilibrium is equal to the formal concentration minus x, while both the hydronium ion and A minus ion have a concentration of x. Now we can return to our Ka expression, which is equal to the product of H3O plus concentration times A minus concentration divided by HA concentration. From our table, we find that this is equal to x squared in the numerator over f sub HA minus x in the denominator. But looking at our table, we see that x is nothing more than the equilibrium concentration of the hydronium ion, and we can substitute this into our Ka expression, which now reads Ka is equal to the hydronium ion concentration squared divided by the formal concentration of HA minus the hydronium ion concentration. Therefore, if we know the pH of the solution, this allows us to calculate the equilibrium concentration of hydronium ion, and we can then use the above equation to solve for Ka. Let's work an example. You have a 0.075 molar solution of glycolic acid in water, and this solution has a pH of 2.48. Calculate the value of Ka for glycolic acid. The first step in this problem is to determine the concentration of hydronium ion from the pH. Recall from the previous lecture that the concentration of hydronium ion is equal to 10 raised to the negative pH power. This becomes 10 to the negative 2.48 power, or 3.3 times 10 to the negative 3 molar. The next step is to substitute these values into the Ka expression from the previous slide. Recall that Ka is equal to the equilibrium concentration of H3O plus squared divided by the formal concentration of the glycolic acid minus the hydronium ion concentration. This becomes 3.3 times 10 to the negative third power squared divided by 0.075 minus 3.3 times 10 to the negative 3, or 1.1 times 10 to the negative 5 divided by 0.072, which gives a Ka value of 1.5 times 10 to the negative 4. Now let's look at weak bases. We learned in a previous lecture that the relative strength of a base is determined by how well it associates in water to accept a proton. A strong base will completely level in water, meaning that all base molecules will accept their protons. A weak base will only partially associate in water. Most of the weak base will stay in its deprotonated form. The extent of association of any base is determined by the value of its base association constant, Kb. Again, as with any K, the larger the value, the farther it lies toward products. So the larger the value of Kb, the stronger a base is and the more it tends to associate. For example, strong bases have a Kb value considerably greater than 1. If we consider the hydroxide ion, it has Kb approximately equal to 55. While the hydride ion, H-, has a Kb value approximately equal to 1 times 10 to the 21st power. Most bases, however, have a Kb less than 1. These are considered to be weak bases. For example, ammonia has a Kb value equal to 1.8 times 10 to the negative 5, while pyridine has a Kb value of 1.7 times 10 to the negative 9. Because the Kb value for ammonia is larger than the Kb value for pyridine, we consider ammonia to be a stronger base than pyridine. All weak bases exist in a state of chemical equilibrium. Let's consider the reaction of the weak base B with water. We have B reacting with water to form an equilibrium, the Hb plus ion plus hydroxide ion. The equilibrium constant expression takes the form Kb is equal to the concentration of Hb plus times the concentration of hydroxide ion divided by the concentration of B. As before, there are two types of calculations we can perform. If we know information about the equilibrium concentrations, we can calculate the value of Kb, or if we know the value of Kb in initial concentrations, we can calculate the equilibrium concentrations and the pH. Again, we will focus on this first type of problem. Again, recalling from the previous chapter, if we know the initial concentrations of all species in an equilibrium reaction and the equilibrium concentration for at least one species, then we can calculate the value of the equilibrium constant. This is true for weak bases. If we know the formal concentration of the weak base and the value of the pH, then we have sufficient information to calculate Kb. This analysis is identical to that for a weak acid, so we will skip the ICE table and directly write the equation for solving for Kb. In this case, Kb is equal to the equilibrium concentration of hydroxide ion squared divided by the formal concentration of the base minus the hydroxide ion concentration. The only real difference in this calculation is that we must first convert pH to pOH in order to calculate the hydroxide ion concentration. Let's consider an example. You're given a 0.015 molar solution of the weak base methylamine in water, and this solution is determined to have a pH of 11.41. Calculate the value of Kb for methylamine. Our starting point in this calculation is to first calculate the pOH from the pH. Recall that the pOH is equal to 14 minus the pH, or 14 minus 11.41. This gives a pOH value of 2.59. The next step is to calculate the hydroxide ion concentration from the pOH. Again, the hydroxide ion concentration is equal to 10 raised to the negative pOH power, or 10 to the negative 2.59. This gives a hydroxide ion concentration of 2.6 times 10 to the negative 3. Lastly, we can use the equation from the previous slide and substitute in our values. In this case, Kb is equal to the concentration of hydroxide ion squared divided by the formal concentration of the methylamine minus the hydroxide ion concentration, or 2.6 times 10 to the negative third squared divided by 0.015 minus 2.6 times 10 to the negative third. This gives 6.8 times 10 to the negative 6 divided by 0.012, or a Kb value of 5.7 times 10 to the negative 4. As we have seen, the values of Ka and Kb are typically very small numbers requiring exponential notation. This is similar to our hydronium and hydroxide ion concentrations in solution. And likewise, in order to simplify this system, we often employ the p-scale, as with pOH and pH. By definition, pKa is defined to be the negative base 10 log of Ka, and pKb is defined to be the negative base 10 log of Kb. Let's look at two examples. First, butanoic acid has a Ka value of 1.5 times 10 to the negative fifth. What is the value of pKa for butanoic acid? We begin with our definition. pKa is equal to negative log of Ka, or, in this case, the negative log of 1.5 times 10 to the negative fifth. This is equal to 4.82. Secondly, let's look at the weak base morpholine. It has a Kb value of 2.3 times 10 to the negative 6. What is the value of pKb for morpholine? Again, pKb is equal to the negative log of Kb. This is equal to negative log of 2.3 times 10 to the negative 6, or 5.64. Now let's look at the relationship between Ka and Kb. Just as there is a strong relationship between pH and pOH of a solution, there is a very similar relationship between Ka and Kb for a conjugate acid-base pair. It is important that you remember that this relationship is only true for conjugate pairs. To investigate this relationship, let's begin by considering the reaction of the weak acid HA with water. Recall that this is HA plus H2O forming hydronium ion and A- in equilibrium. The Ka expression, as before, is Ka is equal to the product of the hydronium ion concentration and the A- concentration divided by the concentration of HA. Likewise, the conjugate base, A- has its own base reaction. This is A- reacting with water, forming an equilibrium HA plus the hydroxide ion. The Kb expression for A- is now Kb is equal to the concentration of HA times the hydroxide ion concentration divided by the concentration of A minus. Recall from the previous chapter that when we have two equilibrium reactions, we can add them together to generate a third. So let's add together our HA acid reaction with our A minus base reaction. Notice that the HA and A minus occur on both sides and therefore cancel. When we add them together, we end up with two waters forming an equilibrium, a hydronium ion and a hydroxide ion. But notice that this combines to generate the autoionization equation for water. This means that the product of the equilibrium constants equals the ion product constant for water, or Ka times Kb is equal to Kw. This expression can be easily verified by using the definitions of Ka and Kb. Let's begin by multiplying the expressions together. We get the hydronium ion concentration times the A minus concentration divided by the concentration of HA for Ka times the HA concentration times the hydroxide ion concentration over the A minus concentration for Kb. When we combine these terms, we get the product of hydronium ion concentration, A minus concentration, HA concentration, and hydroxide ion concentration in the numerator, and the product of HA times A minus concentration in the denominator. We can immediately see that the HA and the A minus concentrations cancel out, leaving us with the hydronium ion concentration times the hydroxide ion concentration. But this is just equal to Kw, and we have verified the previous expression. The consequence of this is that we can calculate the K for any conjugate if we know the K value for the weak species itself. We have to invert to solve, and this gives two different possibilities. First, we can divide through by Ka, which says that if we know Ka for a weak acid, we can calculate Kb for its conjugate base as Kb is equal to Kw over Ka. In the other case, if we have a weak base, we can calculate Ka for its conjugate acid by inverting and finding that Ka is equal to Kw divided by Kb. Let's look at two examples. First, the weak acid formic acid has a Ka value of 1.8 times 10 to the negative 4. What is the value of Kb for its conjugate base, the formate ion? We're solving for Kb, which is equal to Kw divided by Ka, or 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 4. This gives the Kb value of 5.6 times 10 to the negative 11 for the formate ion. Next, the weak base ethylamine has Kb equal to 4.8 times 10 to the negative 4. What is the value of Ka for its conjugate acid, the ethylammonium ion? This time we're solving for Ka, which is equal to Kw divided by Kb, or in this case, 1.0 times 10 to the negative 14 divided by 4.8 times 10 to the negative 4. This gives a Ka value of 2.1 times 10 to the negative 11. As the last topic in this lecture, let's consider the relationship between the values of pKa and pKb for a given conjugate pair. Hopefully it's clear that there's a very similar relationship as that between pH and pOH. We begin with our Ka and Kb relationship, and then take the negative log of both sides. Recall that Kw is equal to Ka times Kb, and so we get the negative log of Kw is equal to the negative log of Ka times Kb. We now apply our product rule for logarithms on the right-hand side, and we get negative log of Kw is equal to negative log of Ka plus negative log of Kb. But we now know what each of those terms represents, and we get pKw is equal to pKa plus pKb. This is a general relationship. Recall that at 25 degrees Celsius, pKw is equal to 14, and so we have 14 is equal to pKa plus pKb. This concludes the lecture on the relationship between Ka and Kb. There are several important ideas that we learned during this lecture. First, Ka indicates the relative strength of acids, while Kb indicates the relative strength of bases. Second, if we know the pH of a solution and the formal concentration of the species, we can calculate Ka or Kb for the acid or base species present. Third, the values of Ka for a weak acid and Kb for its conjugate base are tied by Kw. And lastly, the values of pKa for a weak acid and pKb for its conjugate base are tied by pKw. In the next lecture, we will see how to perform calculations on weak acids and weak bases to determine the pH of the solution.